So now that we have some idea of what infinity and an infinitesimal is, it's time to take these ideas and try to find a limit. Now I know I haven't defined what the limit is yet, but we're going to develop that by first looking at some tables and some graphs. And so that's what we're going to do in this section, is using tables and graphs to find a limit. But before we do that, we do need to deal with some notation. So, if you've been noticing, I've been using the word like goes towards or approaching a lot. And this gets a symbol. The arrow means approaching. So we would read this statement as x approaches 2. And approaching has to be done in a very specific way. How we approach 2 has to be done in a way such that we get infinitesimally close. And so here's where the infinitesimal comes in. X has to be chosen so that it gets closer and closer and closer to 2, forever closer to 2. And I do want to stress here that technically, getting close to 2 is not good enough. So let's say you're only 1 away from 2. 1 seems pretty close, but that's not good enough. What we mean by approaching 2 is that you have to get infinitesimally close. Nothing else will be satisfied. You have to get infinitesimally close. So let me give you some ideas of how you would do that. And as a last statement I want to throw up here, that in this context here, x approaches 2, is that x is not a finite quantity here. In this case, x is now a forever changing quantity, and that it's getting closer and closer to 2. So let me use Excel here and just demonstrate some numbers that would express that idea. So let's say we want to approach 2. And now what would be some numbers that would get across that idea? Well, we could start with, say, 1.9, and then maybe 1.99, and just keep tacking on some 9s here forever and ever and ever. And we can put as many 9s as we want there. Oops, Excel actually put that to 2. We can put as many 9s as we want there. And this expresses the idea of approaching 2. And notice, we can't express the idea without using many, many numbers. So let's try something else. Say we want to approach the number 6. What are some numbers that would express this idea of approaching 6? Well, how about 5.9, 5.99, and just keep throwing more and more 9s on there. And this is expressing the idea of getting closer and closer. So how about, say, we want to approach minus 2. Now, if you look at the previous examples, I've been approaching from the left on a number line. So I approached 2 from the left. I approached 6 from the left. So let's also approach minus 2 from the left. And we want to do this in a way that expresses this idea of getting infinitesimally close. So from the left, we could do something like minus 2.1, minus 2.01, minus 2.001, and just get more and more zeros in there to express the idea that we're getting closer and closer to minus 2. Something else that's important to notice here is that when I approach 2, that the numbers never actually become 2. And this is part of what approaching means. Approaching means you get forever closer. It doesn't mean you become it. It only means you get forever closer. So when I approach 2, we never actually get to 2. When we approach 6, we actually never get to 6. And same with minus 2. As we approach minus 2, we actually never get to minus 2. Remember again, this is the infinitesimal. We are going to get forever closer. And since we're getting forever closer, means we never really become that number. We just get really, really close. So this approaching from the left, which is what I did with these 3 examples, brings up another piece of notation we have to introduce. And let me just bring in a PowerPoint here so I can bring in a graph here. So here we have just a standard graph. And let's say we want to approach 1. And we can approach 1 from the left. So we could take numbers from the left of 1 and approach it infinitesimally. And we call this then approaching from the left, and then we signify that with a minus sign in the exponent of that number. And now here the minus sign, that's all it means. It doesn't have any exponential properties. It doesn't mean an exponent. It specifically means here we're going to approach from the left. And we could also approach this from the right. And from the right then gets the plus sign in the exponent position, the superscript. And again, this means choosing numbers like 2, and then 1.9, and then 1.2, and then 1.1, 1.001, 1.0001, and getting closer and closer to 1, but from the right. So let's do that again for the problems we just did. So technically here, we're approaching 2 from the left. So let's do this again, but let's approach 2 from the right. So that means we're going to start with something that's larger than 2. So something that's larger than 2, say 2.1. And now we're on the right of 2, on the right side of it, and so we want to move in closer and closer. So say 2.01, 2.0001. And again, we can start stacking in as many zeros as we want in there. We're expressing the idea that we're going to get closer and closer to 2, but from the right. Let's check this one out. This one again is technically from the left. So let's do that one now, approaching from the right. So what's a number to the right of 6? Well, how about 6.1? And now we want to get closer and closer to 6. So say 6.01, and then just start getting a bunch of zeros in there. And we're expressing the idea of getting closer and closer to 6, infinitesimally close, but now we're doing it from the right. And let's do this last one. We did previously. We approached that from the left. And let's approach minus 2 from the right. So what's a number that's to the right of minus 2? Well, that's where we would have a number like minus 1.9. So we're to the right of minus 2, and now we want to get closer and closer to minus 2. So that would be something like 1.99. And then start stacking some 9s in there. And so we're expressing the idea that we're going to approach minus 2 from the right. So again, approaching from the left, if this was 1, Approaching from the left means numbers less than 1, getting closer and closer. And from the right means approaching with numbers greater than 1, but then getting closer and closer. And then both of these have their new notation. So, in general then, we're going to have this expression. So we would write x approaches c from the left. So where c can be any number here. C can also be 0, any number. And the other piece of notation we have here is the plus sign. So we can write then x approaches c from the right. And so now our new notation here is the arrow and sticking this plus or minus in the superscript position here, where you'd normally expect an exponent to be. So there's only one new piece of new notation here. And let's start with how we put all this together with function notation, something you're familiar with. Now, what we do with function notation is we actually then stick on this word lim for limit. And that's what lim means, the limit. And then underneath lim is where we put the approaches statement then. So right here I have the limit of our function as x approaches 0, and I'll say from the right. And so this is putting all our notation together here then. And this is the limit. This is the notation for the limit. So we stick on the lim and the approaches right in front of the function notation. So let's do some examples with this notation. And I will just get rid of this stuff here. And I'm just going to make up some function here. And let's just go with, say, a good old parabola x squared. And so we want to find the limit of x squared as x approaches 0 from the right. So the first thing we want to do here is then create some column of numbers that it represents approaching 0 from the right. So from the right means larger numbers. So say 0.1, and then maybe 0.01, and 0.001. We don't have to have too much structure here, as long as we're representing the idea that we want to get closer and closer and forever closer. So we've chosen our inputs. We've chosen the x approaches 0 from the right. So we'll simply plug these numbers into the function. So we're going to plug this into x squared then. And just using Excel here to get those answers. And here are the answers we're getting. And notice that 1e to the minus 12, minus 14, so that's these are getting to be very small numbers. As x approaches 0 from the right, so this is going to 0 here, we notice by inspection, by simply looking at our table, that the outputs are also going to 0. So this is just from inspection by looking at our numbers. And so then we would say that this limit equals 0. Let's try another one. how about 3x? And let's approach 2 from the left. So we have our function 3x, and we want to find the limit as x approaches 2 from the left. So first, we want to think about what numbers we want to use here. We want to approach 2 from the left. Now, from the left means number less than what we're interested in. So we need a number less than 2, so say 1.9. And now we want to choose other numbers to express the idea that we are getting infinitesimally close to 2. Now that we've chosen some inputs, so again, this is the approaches part, we're now going to plug these inputs into the function and then simply observe what the function is doing. So we're going to do 3 times our input, and then simply observe what's happening to those outputs. So we chose the inputs so that they would be going to 2. And if we look at the function output, we can simply observe here that this is going to 6. So we can see the outputs are getting forever closer to 6. And that is then our limit. Our limit is the number that we approach infinitesimally. So let's try another one. How about we take the limit of 2x cubed minus 4x. And let's approach 97 from the left. Now, the first thing you want to think about are what are the correct x inputs that would represent approaching 97 from the left. So what are some numbers that would do that? And I do want to stress there is no one correct answer here. There's infinitely many ways we could choose these numbers. But from the left means we want something that's less than, so a number that's less than would be 96. And then we want to express that we're going to get closer and closer and closer to 97. We want to express the idea that we're going to get infinitesimally close, forever closer. And once we've chosen some inputs here, we're going to take our inputs then and plug it into the function and then see what the function is doing. So we're going to have 2 times our input, and we're going to cube that, and then subtract off 4 times that input, and we're going to observe what happens. So we chose our inputs so that they will be going to 97. That's how we chose our inputs. Now we're going to look at the outputs. Now we can see the outputs are at least starting to stabilize at 18 here, at 1.8, and we can see the 2 is also starting to stabilize, as well as the 4. The 9 gets repeated, as well as 5, 7. This looks to be going to 1, 8, 2, 4, 9, 5, 8. Now, of course, I don't know this for certain. This is part of the failure of using tables, is this just gives us evidence, suggests what the answer is, but it doesn't prove it. So if you're wondering, is this really the right answer? Well, we're not in a position where we can establish that yet. We're using tables so we can see what's resulting. Now these problems that we just did here, if we actually approached from the other side, so if we approach 0 from the left, we would find that it equals 0. And same for all these problems. So if we approach this one from the right instead, we would find it equals the same, and same here. And you can check that out if you want, but there is no guarantee that approaching from the left and approaching from the right are going to equal. There is no guarantee that approaching from left and right are going to equal. And so let me give you an example of that. Here is a function, e raised to 1 over x. And let's say we want to approach 0. Now, if we approach 0 from the left, so we just follow the function along, and as we get closer and closer to 0, by observing the graph, as we get closer and closer to 0, we can see the function is also getting closer and closer to 0. So our limit from the left is 0 as we approach 0. However, if we approach 0 from the right, now look what the function is doing. From the right, the function is blowing up to infinity. And so the left and the right limits do not equal. So let me state that using our notation. So we have the limit from the left. So we have our minus sign in the superscript there. And then we also have the limit from the right. So we have the positive sign in the superscript there. And now what I'm saying is, if these two limits equal, then we get a new expression. So if the left limit equals the right-sided limit, then this equals this limit statement, where notice the c no longer has a plus or minus sign. When there is no plus or minus sign, this is then called the two-sided limit. So what we've been working with are one-sided limits. So one-sided limits will have this plus and minus in the superscript, and a two-sided limit will not have that plus or minus in the superscript. And again, the two-sided limit means the left and the right equal the same number. So let's do an example, putting all of this notation together. So let's check out. We want to know the limit of 1 over x minus 3 as we approach 5 from the right. So let's choose numbers that would express the idea of getting infinitesimally close to 5 from the right. So that means we're going to start with a number that's larger than 5, and then start choosing numbers that get closer and closer to 5. Now that we've chosen our inputs, we will now simply plug these into the function and observe what happens to the outputs. So, our input, if we look at our input, we can see we are approaching 5 because we chose it that way. And now we observe what the function is doing. We see the function is approaching 0.5. And now this was all from the right. So let's check this out again, but let's do it from the left. And again, we have to choose numbers that express the idea of getting infinitesimally close. And we're going to do it from the left. So we're going to choose a number that's less than 5. So say 4.9. And now we're going to choose numbers that get closer and closer to 5. Now that we've chosen our inputs, we will put these inputs into the function and observe what happens. So again, our inputs, we chose the inputs to approach 5. We chose them that way because the problem told us to do that. And now we observe the outputs, and we can see the outputs are approaching 0.5. So notice, from the right and from the left, both of these limits approach the same value. So we found from the right, we found this is 0.5. We found from the left, this also equals 0.5. When the left and the right equal, we then have a two-sided limit. And so we can take this expression and then write it without this superscript. Now you may be asking yourself, well, what if they don't equal? What if the left and the right limits do not equal each other? So that means we would have this case. The left limit does not equal the right limit. If this is the case, if the left and right limit do not equal, then we say the two-sided limit does not exist. So DNE, popular little phrase to use there for does not exist. So again, if the left and the right equal, then we can write this as a two-sided limit, which means we drop the superscript of the plus or the minus. If the left and right don't equal, then there is no two-sided limit. We say then the two-sided limit does not exist. Now, ultimately going forward into calculus, we are more interested most of the time in the two-sided limit. So the two-sided limit is where we will find most of our value. And a two-sided limit only exists if the left and the right equal. So let's do another example to show that. And I will use the graph that I had up previously. So let me just show that again. So let's do this function here. And let's look at what happens as we approach 0 here. So we're interested in this limit. So e to the 1 over x is that function I had graphed. And let's check out the limit as x approaches 0 from the left. So let's do from the left. And we have to choose numbers that represent approaching 0 from the left. So that means a number smaller than 0. So say minus 0.1. And now we want to represent numbers that are getting closer and closer to 0. And the more numbers you choose, the easier the final pattern can be to see. And especially if you're using Excel, pretty easy to do many number inputs and see what happens. So now that we've chosen our inputs, we will put that into the function and observe what happens. So these numbers are getting so small that Excel can't even handle it anymore. So right off the bat, in our second row here, we're already hitting a number that's 10 to the minus 44. So we're talking, 43 zeros in that decimal place. And so this number is getting so small that it's already broken Excel. But we can see that we are approaching 0 from the left because we chose that. And then we observe that the output is approaching 0. And so by our table, we would then say, well, we see this answer is 0. So let's do the same one. Let's approach from the right. And again, we want to start with numbers to choose. So we're starting from the right of 0, which means a number larger. So say 0.1. And now we want to choose numbers that get closer and closer to 0. And now that we've chosen our numbers, we'll plug them into the function. Oops, we don't know what that quite equals yet. We're going to plug them into the function and see what happens. And this broke Excel as well. So if you look at this, 0.01, this number here is 10 to the positive 43. So that's 43 zeros. Just to give you an idea there, a million is 9 zeros. So 43 zeros is off the charts large. So large that the next numbers then overflowed Excel. So what did we observe here? Well, as we approached 0, we see our function is going to infinity. And infinity can either be answered with does not exist. Well, I'll get into that actually a little bit later. For now, infinity means does not exist. Well, I better not leave it quite hanging like that. The truth is, with this does not exist and infinity, is it really depends on the person you're talking to. And MyMathLab will go between these two on whether you use does not exist or infinity. But if you have infinity as your limit, your answer, then it's just understood that means does not exist. Now, why does infinity lead to does not exist? Because remember, infinity is something that continues forever. And because it continues forever means we can't get forever closer to it. And remember the infinitesimal. When we approach something, we have to get infinitesimally close to it. And this is also true of the output. Notice for all the problems that we're doing that the outputs are getting infinitesimally close to some number. And that happened for all these three cases, except for this one case here with infinity. Infinity we cannot get infinitesimally close to. And since we can't, then we say that this limit does not exist. So what this ultimately means is that you're learning where the limit fails. And where it fails is where we say it does not exist. You've learned one place where it fails. If the left and the right do not equal, then a two-sided limit fails. It does not exist. The other case is if you have a limit of infinity. So if your outputs are approaching infinity, then this is another case where the limit will fail. And these are the two cases you know at this point. The left and right don't equal or approaching infinity. These are our two cases for failure. Now there are some more cases that we'll talk about, but for now, this is it. Only these two instances will cause the limit to fail. So let's check out what this looks like with graphs then. So here's a book problem right from the book. And again, you should check out the e-text through MyMathLab. So here's a problem there. Now we have a graph. So no function is given here, just the graph. And we have 4 parts. So let's look at that first part there. So they want us to figure out what is the limit. So they want us to figure out the limit of this function as x approaches 1. Now, first off, notice the 1 has no superscript. So that means this is a two-sided limit. And that means we have to check from the left and the right and see if they equal. So let's do that. Let's first check this from the left. Oops, that's a subscript. Check this from the left. Now with graphs, in class, I like to draw a little person that walks on the function. Imagine a tiny little person that just walks on the function, like I'm using with my mouse cursor here. And we want to know, as we approach 1, so right here, from the left. So that's this piece right here. And as we walk along the function, and we get closer and closer to our input of 1, we then just look and see where we're standing. As we get closer to 1, we see that we're standing at a height of 1. And so we would say then that this limit is 1. So this function, as we approach 1, an input of 1 from the left, we end up at an output of 1. And that is our left-sided limit there. So let's check out the right side where we put the plus sign here. So now we're going to approach 1 from the right. So now we're on this piece here. Now imagine again you're a little person just walking along this function. As you get closer and closer to 1, what height are you at? Well, you're now at height 0. And so this limit equals 0. Now notice the left and the right do not equal. Thus, our final answer for the two-sided limit does not exist. Again, the two failures for the limit is if the left and right don't equal, or if one of those goes to infinity. Those are the two cases for failure at this point. And so that's our answer for part A. This limit does not exist. So let's check out part B. So part B says the limit of the function as we approach 2. Now notice again, 2 has no superscript, so this is a two-sided limit, which means we have to check the left side and the right side to see if they equal. So let's check the left side. So our point of interest is 2, an input of 2, and we want to approach from the left. So approaching from the left puts us on this piece. And if we were a little person walking along this function, as we got closer and closer to an input of 2, we would find ourselves at a height of 1. And that's the limit. So let's check out the right-sided limit. So now instead of the minus, we got the plus to indicate coming from the right. And I don't know what that equals yet. Let me get that out of there. And so we're going to approach 2 from the right, which means we're on this piece right here. And again, imagine you're a little person walking along. As you get closer and closer to an input of 2, you find you're at a height of 1. And so this limit is 1. And now we recognize the left and the right equal. Since they equal, then the two-sided limit will then equal that number. And so our answer for part B is 1. Check out part C. So we're going to take the limit of the function again, but this time as x approaches 3. Notice again, this is a two-sided limit, so we have to check the left and the right to see if they equal. So let me just stick a minus sign up here to indicate from the left. And let's look at the graph and see what this equals. So 3 is our point of interest, and we're approaching from the left. So imagine you're walking along the function. As you get closer and closer to an input of 3, you would find yourself at a height of 0. And that's the limit. Let's check approaching from the right. So I'll change the minus to a plus here to indicate from the right. Our point of interest is 3. And now we're going to come from the right on the function. So we'll walk along. As we get closer and closer to an input of 3, we find ourselves at a height of 0. And that's the limit. And now we can observe that the left and the right equal. Thus, the two-sided limit exists. And it equals then that number. And that's our answer for part C. The limit is 0. Now notice for part C, notice that an input of 3, they have a hole here, meaning that there's no function value, and they have a dot up here. So they're being a little goofy and trying to say the function is going down and just pops up to this dot and then comes back down again. But the limit doesn't care about that dot. The limit cares about what happens as you get infinitesimally close to 3. The limit does not care what happens at 3. It only cares about what's happening as you approach 3. So let's check out their last one there. They have the limit of this function as we approach 2.5. So again, a two-sided limit. So in order to get this answer, we do need to check the left and the right. These both have to converge to the same value. So 2.5, right in the middle between 2 and 3 here. And we're going to approach it from the left. So if we approach this from the left, this will be a half. Now I know it's a half because rise over run, we have a rise of -1 with a run of 1. So that means we have a slope here of -1 for this line. And so at right here at a half, 2.5, we would be at a height of a half. And that's our answer. Now we do have to also check from the right. So I'll take that minus sign, make it a plus. We don't know that answer yet, so let me get that out of there. Whoops. So 2.5, right in the middle here. And we're going to approach it from the right now. So as we walk along and get closer and closer to an input of 2.5, about right here, we see we're at a height of a half again. And that's our answer. And now again, we can see the left equals the right, which means then the two-sided limit does exist, and it equals that number. So let's try another one. Here's another problem from the book. And just clear this page here. This one's slightly different. In this case, they want us to know if these are true or false statements. So let's look at A. They're giving us a two-sided limit. The limit as x goes to 0. There's no superscript there, so this is a two-sided limit. And they're saying the two-sided limit exists. That's all they're saying, is it exists. So that means the left and the right must equal, and there can't be an infinity. If those two things are not present, then it exists. So let's check it out. An input of 0 is right here. As we approach from the left, we will end at a height of 0. And if we approach from the right, we will also end up at a height of 0. And so A is true. So let's check out B. Again, a two-sided limit. These are actually all two-sided limits if you look at them. So now they're saying the limit, the two-sided limit of the function as we approach 0 is 0. So let's take a look. Here's our input of 0, the y-axis. As we approach from the left limit is 0. If we approach from the right, we also end up at a height of 0. So the left and the right limit equal, and they equal 0, which means then the two-sided limit is 0. And so that's true. Wow, this Word document is being really goofy. Not quite sure what's going on there, but true. Check out C. So now we want to know the limit of the function as we go to 0. Does this equal 1? Well, that can't possibly be true because we just concluded B is true. So any other answer would have to be false. But let's take a look at that really quickly. 0, as we approach 0 from the left, we end up at a height of 0. As we approach from the right, we end up at a height of 0. This limit is 0. This limit is not this dot up here 1. And again, remember, the limit doesn't care about some individual value like this. The limit will never equal, the input will never equal our point of interest. So we actually never get to 0 here. Let's check out the next one. Now they're asking us if the limit of this function as we approach 1 is this 1. So let's take a look at an input of 1. Here's an input of 1 right here. As we approach from the left, that's right here. So as we walk along this function and we get to our input, we find we are at a height of a -1. So the left limit is -1. If we look to the right and we follow the function, as we get closer and closer to the input, we are now at a height of 0. So the left limit is down here at -1. The right limit is up here at 0. These do not equal, and thus the limit does not exist. And so D is false. There is no limit there is no two-sided limit at 1. Again, because the left and the right do not converge to the same value. We say there's a gap here, or a jump discontinuity, because the function here is disconnected. And this disconnection will always cause the limit to fail. So let's check out E. And really quick there, I said these disconnections will always cause the limit to fail. That is precisely because the left and the right won't equal. So let's take a look at E. They're now asking us if the limit at 1 is 0. Well, it's not. We've already concluded the limit at 1 as we approach 1 doesn't exist, so it's certainly not going to be 0. It still is false. Let's check out F. We want to know the limit of any number, so they're saying C, any number, exists at every point C in this open interval of -1 to +1. So here we are, here's -1, and here's +1. So they're asking us, in this interval from -1 to +1, so the function is this line here, jumps to this point here, and it comes down here again. Is every point here, does every point have a limit? And, well, we have to think about then what causes the limit to fail. What causes it to fail if the left and right do not equal, or if there's an infinity. So I think the easiest thing to see here is that there's no infinity here. This function is not just blowing up off the charts. So there's no infinity here. So now we need to determine if the left and right always equal here. And they do. So how do we know? Well, if we look at this line here, imagine we have a person standing at the left here, a little person, and a little person standing at the right. as they walk towards each other, they will always meet because this line here is continuous. So if they walk from the left and the right and walk towards each other, they will always meet, no matter what point we pick here. And the same is also true for this right side. Now, I just want to compare this to these two parts, this piece here and this piece here. Now imagine we have a little person starting at this point and they're going to walk towards 1. And we have another person here that's going to also walk towards 1. Now notice as these people try to walk towards each other, they will not meet. One person will be stuck up here and the other person will be stuck down here. They will not meet, and so the limit doesn't exist. And if we look at this between -1 and 1, we can see at every point two people will come together and meet. The only potential trouble here would be at 0, but we've actually concluded that this limit at 0 is already 0. So every point here, and the main logic here that allows us to conclude this is that this is a solid connected line. And if you have a solid connected line like this, then the left and the right will always converge to the same point. So that is F, and that is true. The limit exists at every point between -1 and 1. As a matter of fact, the only place the limit doesn't exist is at 1. And again, you can see if two people try to walk towards each other, one is stuck at 0 and one will be stuck at -1. They don't meet. So let's check out G. The limit of 1 does not exist. And that's funny because I just said that. The only place the limit doesn't exist here is 1, because these people would not meet if they tried to walk towards each other. So G is true. The limit does not exist as we approach 1. Now these last questions here are just straight function notation questions. So for instance, what is the output of the function at 0? Well, at 0 is now when this point, this goofy point right here comes into play. So the output of the function at 0 is actually 1 right here. And so H is false. Now notice I, it's at 0 again, but now it's saying it equals 1. And this is true. This function, when you plug in 0, this dot means here's the output, and that output is at 1. So I is true. We look at J. When we plug in 1, does our function output 0? Well, let's look at 1. Now remember from your algebra days, hopefully, that the open circle means there's no value there, and the closed circle means that there is a value here. So when we plug in the number 1, the function is right here then at this closed circle. And the function is outputting 0. So f of 1 is 0, and so J is true. And then finally, f of 1, they're saying, does this equal -1? Well, here they are. They're trying to test you to see if you think this open circle means a function value. When it does not, the open circle means there's no function value there. And so K is false. So this concludes then our first lecture for section 2.2. And 2.2 is rather long, so I am breaking it up into 2 parts. So this will be 2.2 part A, and then the next lecture video will be on 2.2 part B. And I'm also going to upload a video where I will do some homework problems right out of my math lab, so you can just gain some confidence and that you are doing things correctly. So if you want to check out that video, that'll be the next one right after this.